points? And the answer is yes, partially. So here are these resolvers of Google, obviously. Again, they're quite easy to spot. We see RSA MD5 or returning a surfail. They're quite easy to spot. Other ones are also interesting. So here we see that RSA MD5 is considered as insecure. And these are resolvers that are probably younger than 2012, because around that time the new OARC was published. So we can at least narrow down the resolvers that are used. That might be a bind version which is younger than, older than 9.9.0, because in this version they added the support for Ghost. So that could be also an idea to point that down. And this one was an interesting case as well. So these ones were resolvers of Power DNS and not, and they returned a surfail for all the algorithms that they didn't support, which is probably not the behavior you want. Colleagues of mine reported that behavior and they fixed that, so that shouldn't happen that much anymore, but we still find a couple of vantage points or resolvers that have this behavior. Now, another side effect that we measured was, okay, what happens if a signature expires? And that's kind of a measurement that we were able to do because we kind of messed up our automatic re-signing. So we had a period of 4 hours where where our signatures expired, basically. So that was kind of unfortunate, but from a researcher's point of view, that's great. So we had something to look into. And we can basically look at two interesting things here. Maybe the first one is the resolvers below that at some point returned a surfail at some point for the validly signed domains. And what I looked at is how long did they still respond with a valid, or consider our test domain still as valid even though the signature was expired. And we can see that over 60% of the resolvers were returning even 20 minutes after the signature was expired, still with a valid response. And I think this is a behavior you want. Another spike was, another interesting thing was the one on top, which are the resolvers that keep on validating. And I looked a bit into what resolvers were there. Some of them were Google's. We found a couple of French ISP frees us, and for us as a Dutch organization, also from the Dutch ISP Access for All, a couple of them. And we know that, for example, Unbound considers expired signatures valid for up to 1 day, I think. So these resolvers might be unbound. But overall, our period of was only 4 hours where we had expired signatures. So future work might be to look at bits into more detail what was actually happening there, and see how long actually these resolvers consider them as secure. Now, lastly, we want to improve our vantage points. As I showed, our vantage points are rather limited. We have the Illuminati network, we have the network of RIPE Atlas, but we would like to have more insight. So that's like a request for you, if you guys would be willing to run maybe a small shell script that periodically queries our test domains from your resolvers and which reports the data back to us. I haven't finished the script yet, but that should be finished quite fast. And if you're interested, just come talk to me and check things out. And then maybe we can see how we can collect this information better. Yeah, that was basically it. We have all the information are available on the website. We also have a small live feed where you can track how these different RIPE Atlas probes behave on a beautiful map, so you can see whether RIPE Atlas probes fail at some point. In the slides, I also have more fingerprints of DNS Sec behavior, so you can check out whether you can identify some other interesting resolvers there, and if you have, I can use it as a quiz or anything, and you can tweet me if you have an idea which resolvers that might be. And yeah, that was basically it, and I'm now happy for some questions.
Paul Hoffman from ICANN. First, thank you. Thank you, thank you, thank you. This is wonderful. I suspect it's going to continue to be wonderful for quite a while. We at ICANN did actually watch for more than 48 hours of that TTL, just so that everyone knows. We were actually getting data from 10 of the 13 root server letters, and it continued to be completely flat. Okay. So what you saw in those first minutes was what we saw with lots and lots of data going on. Yeah, it was all continued flat. And the last thing I want to say to the room is, your last, on the previous slide, you said you're going to let us have a way of helping contribute data. Hey, everybody, let's help.
Okay, thank you.
Petr Špaček, CZNIC. I have an update for our fingerprinting slides because we fixed the bug, so it's powered DNS.
Yeah.
Hi, Olar Williamson, Cloudflare. Can you go back to the slide where you're returning the expired stuff? Keep going back. That one. Is it possible there might be an implementation that is not applying their logic to cache, how long they cache stuff? So they just store it for the whole TTL instead of capping the TTL by the expiry of the signature?
So the TTL of a signature was very short.
Yeah.
So they should, yeah, maybe they just ignore our short TTL. That could be something, but I think overall they, yeah, that the caching should not be an issue there.
So basically I'm asking if you can fingerprint the people who are doing this, if they're all the same implementation.
I'm not sure if I can get your question, sorry.
Yeah, well, is it one, if you're fingerprinting your resolvers,
yeah.
Are there certain resolvers that are doing this
yeah.
more than others?
That's definitely future work, yeah. That would be interesting to see if you can correlate that behavior with the fingerprint. Yeah.
Thank you.
Okay, thank you.
All right, thank you. So Matt Poundsett, could you please stand up? We're going to be doing a Pgp signing party, like right during the, when are we doing it? Tomorrow, okay. And thank you.
Hi, everyone. So we're going to be doing our usual PGP key signing. I believe it's scheduled for tomorrow at lunch. Is that right, Keith? Yeah. So tomorrow at lunchtime. There's an email address that we had up just before, which I think we'll be able to put up again. I believe it's pgpsign@dnsoarc.net, where you can send keys that you'd like to have participate in the key signing. We're going to do things a little bit different this time than we have in the past. The way we're going to do it this time is I'm going to collect all the keys, produce a key ring. Just before lunch tomorrow, I will come up and put up a few slides with a hash of the key ring of all the participating keys. This way you can download the key ring, hash the file, compare it to the hash that I've published. And it'll be a much simpler, much faster way for everyone to verify that all of the keys that they have in the key ring are the same keys that I've published. From that, you can then go around and find the individuals whose keys you're going to sign, get them to attest that the key in the file that they downloaded is the same as the key that they contributed. And the whole process will be a lot faster and a lot more open in terms of when people can do things. We don't need to all sit in a circle and read out our key ring, our fingerprints at the same time. So we're going to give this a try, and hopefully it should be a little bit more speedy and fluid than it has been in the past. So yeah, so the highlights there are, please, if you want to participate, get your keys into this email address by the end of first break tomorrow. After that point, I'll have to. Do we have that up? I think it was in. Yeah. Yeah, okay, here it comes. So after break tomorrow, I'll compile the key ring and fingerprint the key ring and put together some slides so that I can communicate the hash of the key ring to everyone just before lunch. So yeah, so All right, yeah, I believe it was pgpsign@dnsoarc.net. I think, yeah, we'll find the slide and get that up at some point before the end of the day. So, if anyone has any questions about how this is going to work, got a couple of minutes now, I think. All right. Otherwise, find me at break or something if you have any questions. Thanks very much.
Okay, thanks, Matt, for stepping up to do that at the last minute. Just a couple of quick announcements. We're doing things slightly differently. Usually at the fall OARC workshop, we do the AGM first and then the rest of the workshop. Just a quick reminder that we're experimenting with the AGM at the end of the workshop. So the public workshop stops at the afternoon break tomorrow afternoon, and then it will only be OARC members that may participate in the room. Don't forget to pick up your social tickets from the registration desk. The other thing that I should do is to thank our sponsors, in particular ICANN and VeriSign, who are making a major contribution to the cost of this workshop. I'd also like to thank Comcast and Thousand Eyes. Thousand Eyes have got a booth outside. You want to get a t-shirt from them, and also Influx. So we will restart in approximately half an hour at 11:30.
Good morning. Welcome to our second session for today. We're going to start with Samir, who is an engineer working at LinkedIn. Prior to his LinkedIn experience, he worked at Yahoo on their DNS platform. He loves the internet. He runs his own AS number, 49072, if you want to peer with him. And he deploys 20 POP Anycast networks as a weekend project. So, Samir.
Hello, everybody. My name is Samir. I'm an SRE at LinkedIn on the Edge Performance team. Today, I wanted to share some of the strategies that LinkedIn uses to improve DNS availability. So DNS is heavily used at LinkedIn for traffic engineering. We have a diverse set of POPs across 5 continents that proxy the base page back to our data centers. We also have 5 CDNs, so 4 external third-party CDNs, including 2 in China. And then we also run our own CDN. And so we use GeoIP and real user measurement DNS to steer our members, all with 5-minute TTLs. And I have another talk this afternoon. I'll be talking about real user measurement DNS. I'm just plugging the talk now. So I wanted to start off with a short story. October 21st, 2016 was an end day. And an end day is generally a Friday at LinkedIn where you're encouraged to decline meetings and invest in yourself for the community. And our team had decided to go out and play soccer that day. We'd planned to play soccer in Mountain View Park. And unfortunately, on that morning, DNS, our DNS provider, and the provider of many, many other key sites was attacked. And what made this attack unprecedented was the size of the attack. Dyn had thwarted hundreds of attacks prior to that, but this is the first time that they were impacted. This is what the 4 Dyn name servers look like from catchpoint monitoring. We can see the 3 clear attacks, one in the early morning, one in the late morning, and one in the afternoon. So show of hands of anybody who was affected by the Dyn attack in any way, shape, or form. All right, I see a lot of hands. So yet that day, even though a lot of popular sites became unavailable at different parts of the day, LinkedIn was virtually unaffected. In fact, the team looked at these graphs and they still made a call to go out and play soccer. So why were we all freaking out? And so the answer is simple. This type of DDoS had happened 5 years earlier. And so our solution was simple. We just added another DNS provider. And having 2 DNS providers is awesome because instead of 1 set of name servers, you have 2 set of name servers running off independent hardware, software, networks. And so even though virtually a lot of sites were out, NS1, our other partner, was able to carry us flawlessly through the attack. And so what I wanted to do was actually step through that day with data to show you exactly what happened inside of browsers. So just so we're all on the same page, our members never talk to LinkedIn DNS. Instead, they use a local cache. Could be the router, could be a recursive. And it is these recursors that talk to LinkedIn DNS. And the further upstream the query goes, the more time it takes. Now, built into browsers is the navigation timing API, or also the resource timing API. And that allows us to collect very specific metrics about what happens in our members' browsers. And so as they navigate the site or use the app, we can actually figure out exactly how DNS looked like during the attack. And so what I wanted to do is now show you this data. So this is the 90th DNS times every day in the US. It's practically 0, and that's because DNS is cached. And so our members are sending us a lot of data with that number zeroed out. So what we do is we take out all the zeros and we plot the non-zero DNS lookup times. And we end up with a graph like this. So this is the week prior to the attack for 24 hours. And the 2 things I want to point out is that during peak times, DNS lookup times are generally low because caches are warm. And then in the middle of the night, DNS times are relatively higher because caches are colder. So anything else I want to say on this slide? All right, so now the Friday of the attack, this is what DNS times look like inside of our members' browsers and mobile devices. So we can see the first attack, we can see the second attack, we can't really see the third attack. But what I want to point out is that from a latency standpoint, our users didn't really experience anything out of the ordinary. Sure, there's a peak up there, but that peak's actually lower than what they would experience if they came to the site in the middle of the night. Next up are our traffic levels for that day. They're actually higher that day. There are also no member reports of site issues. And so I think this is phenomenal proof that having dual DNS absolutely helps with availability. Now for edge teams who operate DNS and would like to have a second provider, here are just some tips you should know about. So first of all, there's basic zones and advanced zones. The basic zones are the bind zones we're all familiar with, that we all love. They tend to be static, and if you have that, then everything's pretty straightforward. At LinkedIn, we have a lot of advanced zones, so things that have GeoDNS, health checking, weighted round robins, and they tend to be very dynamic. And so things get a little complicated here. So yeah, the first thing you're going to run into is keeping your zones in sync. And so if you have basic zones, it's pretty straightforward. You run AXFR, AXFR. We have a lot of advanced, and so it's a mix of basic and advanced records. And so we built a DNS tool that lets us do all the basic records. And so, you know, we have SRE teams at LinkedIn and mail teams that can go in and make their changes without interrupting our team. So for advanced zones, they're going to differ from vendor to vendor. You're going to have to manually sync things for a while. We used to do this for years, just manual sync between our various providers. We now have a DNS sync tool that pulls from one provider, normalizes it, and pushes it in the other provider using APIs, so it's all automated. The next thing you need to know is you need to alert on zone diffs. So because you're running primary, you'll effectively sometimes have zone diffs. We used to have a simple Perl script that used to diff the zones. Now we have a little more advanced Python application, but it's still email alerts. Other things you should know is you need to use the lowest common denominator features between your providers. If you run a mixed mode environment, it's going to be complicated. There's going to be tech debt, so we don't recommend that. You cannot have DNS Sec with advanced zones. As you know, DNS Sec signs the RR sets, and they will be different between providers because the zones coming out of advanced zones are non-standard. Your SOAs won't match. With advanced zones, with health checking, the SOAs increment at different rates. And so you can actually write automation to sync the serial numbers regularly, but again, it's overhead that we haven't done. So we've been running different SOAs on all our zones for years now. Zero issues except for the Icelandic registry. They came to us, they ran a script, it showed the SOAs were different, and they required us to actually go single provider for the Icelandic domain. Every other registry hasn't had an issue with it, so just be aware of that. And then if you're being attacked and your name servers are down completely for one provider, don't undelegate it. It's okay, nothing bad will happen. Maybe it's a ruse, maybe they're trying to get you down to one provider where they can DDoS you. So, you know, if one provider's down, that's okay. So what I want to talk about is this IETF RFC proposal. So the idea here is sometimes recursive resolvers can't talk to the authoritative. And we really care about this at LinkedIn because our TTLs are so short. And so it's very important that the recursives maintain and hold on to a record for us even if they can't talk to the authoritative. And some recursives already have this sort of feature. So Bind 9.12 already has a patch written by David C. Lawrence, who's here in the audience. I've not met you yet, but I will at lunch, I'm sure. Unbound has also some sort of stale TTL features. AnswerX from Akamai also has that feature, so does OpenDNS. So, so for closing thoughts, all I want to say was that if you're running mission-critical services that just can't go down, consider using dual DNS. A lot of Bay Area companies are now dual DNS, and there's many more planning to become dual DNS. And if you have any questions about you know, moving from single DNS to dual DNS, especially with advanced records, I encourage you to reach out to me. That's all I had for today. Thank you.
Questions?
Paul Hoffman from ICANN. Quick question. You zoomed through it, but it sounded like you do a lot of your sort of own DNS telemetry in JavaScript in everyone's browser in order for you to find out when you should be moving such. Is that what you were indicating?
That's correct. We use JavaScript to pull the metrics from the browsers. The browsers have their own clocks that do all the timings. Right. We don't actually do JavaScript timers. We don't recommend those at all.
Ah, okay.
Those will be different on various devices, especially in third world markets where the devices are not as powerful. The metrics will be very skewed. Do not use JavaScript timers, but we use JavaScript to read the metrics off the browsers and the clients, yes.
A presentation or a paper on how you do that and how you know which browser you're on and which metrics you're getting would be greatly appreciated.
Absolutely. We have a blog, and if you come reach out to me after, I'll send you the link.
Thank you.
All right.
Say, Ed Lewis from ICANN. I wanted to ask about the not being able to do DNS Sec in the advanced zones. How concerned are you about that? Let me put it that way first.
Oh, can you ask your question again?
Do you think that's a big problem, that you can't do DNS Sec in advanced zones, or do you think it's just it's the way it is?
Oh, so the question is, are we concerned about DNS Sec?
Are you concerned about it in the advanced zones? I'm saying, would you like to solve that problem is what I'm asking.
Oh, yeah, absolutely. LinkedIn isn't currently concerned with DNS Sec, but of course we would love DNS Sec, and that is a blocker. So if we could solve that problem and somehow have a uniform standard for all these features across zones, it would absolutely help us, yes.
Because the reason I'm asking is I used to work for a place that did advanced zone serving, and we thought about what happens when we have customers like you coming to more than one provider. I don't work there, obviously, now. And the question was, how do you let people, what measure they need to do? And I think it's possible to do that, but it's a matter of how much you want to spend time in trying to fix that. And I think you want to talk on it too, so I'm going to let Oliver follow up. He's a lot rougher than I am at the moment.
Okay, all right, bring it.
Yeah, can you go back to that slide where you talked about the DNS Sec? Sorry.
Sure.
Oliver Gomez on Cloudflare again, sorry.
No, that's fine, absolutely. You want the slide about DNS Sec?
Yeah.
Yes. I think it was this one. No.
No, it came
I'll
after
find
that.
There we go.
Yeah. There are two things in there. The one is that some people think that you can't have a DNS Sec and have multiple providers that are modifying advanced zone. That's not true. You just have to have them use different zone signing key on each side. And yeah, I think, and basically you have to sign on the fly. There is no other way to do it for advanced zone.
Okay.
So signing on the fly works perfectly fine.
So the contents are different, though, of the zones, right?
Doesn't matter.
Doesn't matter?
You sign the answer when you assemble it.
Okay. I'll obviously reach out to you and learn more about that. Thank you.
Okay. You can talk to me afterwards how
Absolutely.
we do it. I am nice.
Oh, sorry. Ed Lewis, I actually had another question unrelated to this. And when you flip through, I remember the sync tool that you have, are you going to make that available to folks in general? Do you think it's generalizable? Do you think it's open sourceable?
No, I'm glad you asked. So for the DNS tool that we build, that's built on complicated LinkedIn libraries that it's hard to open source, but that DNS sync script is very trivial. And so open sourcing it isn't that much work. We've talked about it. We've actually asked people about it, and different people want us to open source. At this point, it's just a scheduling and resource thing. Thank you.
Thank you.
All right, thank you.
Next, we have Wes Hardaker. He's a computer scientist at USC ISE, conducting research on networking protocols, including DNS, routing, and Anycast. He is also responsible for overseeing the operation of vRoot. Could you highlight Wes?
All right, good morning. Still morning, right? I'm Wes Hardaker, and a group of 6 of us put together a new tool for mapping Anycasts that we'd like you to both know about and potentially use in your own environments. And it's called VerfPloater, and I'm mispronouncing that because I don't actually know the pronunciation of it. Not my language. All right, there we go. So our goals with this were really to do a couple of things. We wanted to really map Anycast catchments really accurately, more than has been done in the past. And one of the reasons why I wanted to do this was to accurately study, B's specific Anycast IPv4 catchments. We don't do IPv6 yet, and we'll talk about that later. And the other thing we wanted to do is predict load in advance of changing, because actually, as you know, B just actually went Anycast, and we were kind of curious how much of our load would shift to our new site, and can we make that prediction in advance of actually rolling out to a new site. So as you know, with traditional Anycast probing, what happens is that you would typically send some sort of request out to the service, and then you'd figure out, where it would come back to, and you'd analyze the data and look in a collection. So this is sort of what people do with Atlas, right? They send out a request to the Anycast catchment, they get the reply back, and they figure out where it went to. What VerpLoader does, it uses passive vantage points. So we call them passive vantage points because they don't know that they're part of the Anycast catchment. And the way we do this is we actually send ICMP pings from an address block inside of our Anycast network. So we do this by, I actually sent pings from an address block that we were advertising from both of B's sites, the current site and the future site, and then we watched where the replies came back. So we'd send them from one site, and they would go out, hit the remote destination, and then we'd get filtered back according to how Anycast was routing the replies back. So we were running basically TCP dump at both sites, and then looking at where the replies went to. We did this using an IPv4 hit list. So previous work has actually provided us with a single address per /24 out on the internet, which we figure is the smallest routable block generally. And you get an address. So this is actually a sample out of it. You can look at that website if you're interested in using something like this for your own work, and they'll give you a list of addresses that you can ping. And it's not perfect. We don't get every /24, but we get a good number. So now I'm going to show you a whole bunch of pretty pictures, because pretty pictures are good. So this is RIPE Atlas's coverage of BRoot. RIPE Atlas being, again, one of the ways that people typically do measurement these days. And so you can see that there's all these little circles on there, and we'll dive into the circles in greater detail here in a minute. And you can see that we have LAX and MIA are blue and yellow, and then there's some unknowns because we weren't able to figure out actually where they went. And note that the biggest number here is 277. So one of those little circles is 277 pings went out from that particular spot. Now, this is our coverage of BRoot, and I'll toggle back and forth, and again, we'll go into these in greater detail, but note that the size of the circles has greatly changed. The biggest circle is 185,000 catchment points. So if I shift back and forth, you can see that there's a significantly different coverage. So we're going to dive into, looking at each of these different regions. So if we look at Europe first, you'll notice that Atlas has very good coverage, which is what you'd expect. Atlas was developed in Europe, and everybody has known that I'm not going to say it's biased toward Europe, but they have more nodes deployed in Europe. So our graph actually matches that pretty well from just a pure coverage point of view, right? There's not a huge amount of differences. That's a good thing for Atlas. Atlas actually has reasonable cover in North America too. You can see, a decent number of circles on the left-hand side, but VerpLoader has a significantly bigger coverage. You can see a lot more dots. And again, remember that all of these circles are actually differing in size, so our scale is quite different. But in terms of actual coverage, you can see a lot more pinpoints where we are actually seeing geographically isolated data points. Atlas also has sort of sparse coverage in a lot of other places, like China, for example, where there is no nodes. Because VerpLoader's use of an IP hit list actually goes out and it finds some networks that actually exist in countries like China and gets a reply back, we actually have data for where there's a lot of deployment, or where a lot of regional areas hit our catchments. And again, remember that the different colors in the pie chart show different things. So blue is one site and yellow is the other. VerpLoader also has more coverage in both South America and Africa. If you look very carefully, you'll see that South America in particular has a lot of pinpoints, and Atlas has less. Africa doesn't have a whole lot no matter which system you use because there's not a whole lot of internet deployment there in many regions. We also, in addition to just studying how BRoot was actually being mapped out between its two sites, we wanted to do something slightly more complex. So the next biggest Anycast deployment that we had was actually a test network. So the University of Twente has what they call Tangled, which is a larger Anycast network of 9 different sites. And you can see there's the list of all the different sites. Note that a couple of them do, like the first two, Sydney and Paris, have the same upstream, so that probably will affect the results to some extent. There's obviously more diverse Anycast deployments out there, and I'd love to talk to you if you want to use this software in the end and see the results. There's links to that later on. So here's RIPE Atlas coverage of Tangled, and you can see that there's a lot more colors now in terms of what they're seeing. And here is VerfPloater, so you can see if I toggle back and forth. We say the same sort of spread out. There's a lot of coverage in Europe in the beginning, and then it kind of spreads out to the rest of the world. And again, diving into some differences where we see some interesting differences. So one of the things we wanted to look at is not just, spread differences, but can we actually detect how coverage was mismatched? In other words, look at IAD, which is an olive colored in the VerfPloater chart. And according to Atlas, it looks like the IAD site for Tangled actually almost hits nothing in North America. There's very few things actually hitting the IAD catchment. But if you look at our VerfPloater result, you'll see that there's a whole lot of that olive colored. That's the bottom colored of that bigger circle. There's a lot more coverage of North America, so that's an interesting discrepancy. Australia also shows a sort of a significant change, and again, we're looking at the color differences, especially at the bottom half of Australia. The colors in those circles are almost completely different, which shows that there's a discrepancy for the catchments that Atlas is able to see versus the catchments that we're able to see, but using more /24s. So, as I said in the beginning, the other thing we wanted to do is, can we take all of this extra data, now that we have a huge quantity of IP address blocks out there, and knowing what catchments they're ending up in, can we actually guess at what the load might be once we make a deployment? And so we did this at broot, and we recorded traffic measurements for our single LAX site. So in other words, we took a day's worth of traffic, and for each /24, we predicted how much traffic or what load would be sent to our Anycast catchments based on looking at a single day just hitting LAX, because some sites send us more traffic than others. There's some some /24s that send us nothing, and some /24s that send us quite a bit more, especially in places like India, which has a large amount of NAT deployments, so we actually get a lot more traffic from the /24s deployed in there. And then we ran VerfPloater against a deployed test prefix. Again, this is not the actual B address at the time. This was a test prefix ahead of time. So B was still operating only at LAX, but we wanted to see, okay, if we ran it at both. So we advertised a new prefix and then ran VerfPloater against both. So what did we see? There's a couple of dates. So on April 12th, we saw 2.34 gig queries per day hitting just LAX. And on May 15th, we ran VerfPloater to see what we would get. Oh, sorry, so May 15th is actually after our deployment, and we saw that we had 2.2 gigs heading to both sites, and you can see that a large percentage of it was actually going to LAX. 1.78 gigs were going to LAX, and 0.4 were going to MIA. And this is over a 24-hour period. So VerfPloater load prediction of broot, the red are the unknown blocks, because one of the things that happens is we get data from some /24s that VerfPloater failed to see. So that actually turns out to be 12.9% of our pings they didn't respond to, or we didn't have an address that we could ping them at, but we're still seeing data coming into broot. So that's actually the red in this map. So you can see there's a large number in a couple different places. There's a large red circle on the right-hand side, which memory says that that's Korea, where we were able to ping very little inside of Korea, but yet they send us a lot of traffic. So then we wanted to see, okay, well, if we took that load data and we weighted the Anycast, the pings against the load data, could we actually reflect an accurate mapping and actually predict what load we were going to get? So with the RIPE estimated measurement, we had 9,682 probes on May 15th, and it received 82.4% of the RIPE probes went to LAX. Out of our 3.9 million /24s that VerfPloater hit, 87.8% of them went to LAX. But after doing the weighting, after saying, okay, well, how much, what percentage of traffic do each of these blocks actually send to us, and giving a flat rating for all the unknowns, we were actually changing the prediction from the 87.8 of just, one ping to a weighted load, and it got actually a whole lot closer. So we predicted 81.6%, and it actually came out to 81.4. We consider that a great success, that we were actually able to, merge these two data sources and actually get a really accurate prediction of how much data would arrive at that new site before you actually deploy it. And it also shows that weighting is required, right? If you just do it with random pings to /24s, you'll get a very different result. We couldn't use write, of course, because they really don't have enough /24s to do that sort of weighted analysis. So we also wanted to see, what do we get when we look inside an AS? Can we study traffic catchments within an AS, not just from the outside? And the result is, yes, we can see really interesting things. We can also study routing stability, and you'll have to see that result in the paper. I don't have enough time to talk about it today. But one interesting thing is, depending on how many prefixes a particular AS is advertising, affects how many sites that they will likely see. So there's an interesting relation to basically the bigger ASs that are advertising more sites and are advertising bigger sizes too, which is what this chart is, ends up catching more of your catchments. So they probably have more connections outgoing. This is sort of the same thing, but in terms of size. So the bottom right box shows /23s, the one before that /22s and /21s. And you can see that most of the sites that are advertising very small blocks only hit a single catchment. Whereas as you get up to advertising of /8s and /9s and /10s, you see that that load spreads out across more and more catchments. So really what that amounts to is that 80% of prefixes smaller than /16s only see one catchment site. And so 20% are seeing two or more, but 80% are seeing a single site from a /16. And then larger than that, it starts breaking out into multiple sites. So really quickly, as a sizing summary, VRFplotter sees about 430 times more network blocks than Atlas. And Atlas has some unique blocks, though. It's interesting to note that Atlas, if you look at the bottom row of that table, actually sees 2,079 points, 2,079 /24s that we don't see. So in terms of /24 seen, you can see that Atlas, we saw 8,677, but VRFplotter saw 3.8 million blocks. And out of those, not everything is geolocatable, so all of Atlas's are. That's the nice thing about Atlas, because they record the geolocation ID for each probe. We, unfortunately, don't have geolocation information for some of the /24 blocks, which is why the numbers are different on the right-hand side. VRFplotter is pretty much ready for use, in my opinion. We have papers, the paper that we are recently, that's about to be published, there is a sample of it there that is a tech report, and it's going to come out as an IMC paper soon too. And then we have all of our data sets, so you can actually get all of our ping data and go look at it yourself and do the same math if you want. And then our software is available for use too, which actually does the pings, and it can do rate limiting and all sorts of other wonderful things to make it easy to use, with some documentation on how to do it. And then you can go out and map your own sites. And we'd love to see any results that if you do want to go use it, or you want our help actually mapping your testbed, we'd love, or your real deployed network, we'd love to actually have other sites make use of this. So, okay, thank you.
Do we have any questions for Wes?
Martin Levy, Cloudflare. So I read through the paper that's published in March. It was an M.
Right.
And so I've got a couple of questions. There's forward path and reverse path in the BGP world, which there's nothing that says they should be the same, and in fact they don't. And the paper talks about lots of traffic engineering with communities, which is why you see what you see. So the measurements that you've done and the measurements that are done by RIPE are two valid measurements. But in the Anycast world, isn't it simply the measurement from the end user that really becomes the sort of more overriding, because that's where the query packet will go. And you've measured quite correctly the reverse of that, or at least measured it from multiple points and then correlated which way you think it's going to go. So it's a valid measurement, but life doesn't work that way. And so I'm just wondering, as a commentary from you, how you sort of look at these two data sets and whether you sort of realize that one is, well, they're different, but does one have more relevance in the real world?
Well, that's a very valid point. So, I mean, the thing is that because we are sending out functionally a ping, we are only looking at the replies. You know, the user sending it out, we're treating that as if they sent a request when it's really a reply, right? We are actually invoking the remote thing to give you something. And so you're right, you know, there is a discrepancy between inbound and outbound paths and what happens. We can only hope that most of those, you know, kind of map accurately. And I think that our load analysis, for example, shows that that we got pretty close in terms of what happens. But the reality is because we're only looking at those replies, we're really looking at it as if the end user had sent a packet to us. It just happens to be a reply, not a request.
Yeah. And then, so, sorry. So if I may, a quick follow-on question then. So the other thing that I noticed was, really quickly looking, there's no correlation between the use of transits in the two sites that you have up and running at the moment. And whether it's right or wrong, the mantra that we've always had, and I know others have had way back, if I go back to Rodney's time of first doing this, was equal transits everywhere. And you've done something quite different than that. Can you comment about whether that's, you're going to stick to your guns on this one, but which is fine, because diversity is good, but can you sort of talk about the pluses and minuses of some people in the industry going with consistent, some people going with highly diverse like yourself?
Yeah, that's always I don't have a whole lot to say because we haven't done, we would like to do a much larger, you know, more complex study in terms of both what we advertise. We are about to embark on doing some playing with transits and looking at how we can actually affect balance, and can we use VerfPlotter in order to actually predict some of that as well, and how that we can do, you know, some very careful traffic engineering and have VerfPlotter predict that based on, you know, who we're connected to and where. Our longer term plans are quite complex, and that's one of the reasons that I would love to see somebody else, you know, run this on a different style of network with different connection points to see.
And see if there's more correlation.
Yeah,
exactly. Right.
Hi, Danja Kahnberg, RIPE NCC, inventor of RIPE Atlas.
So don't get me wrong, I wasn't trying to slam right out those.
No, those two things are totally different. I mean, you're basically pinging someone, whereas the Atlas infrastructure is actually a distributed thing that does active measurements.
Well, there's one disadvantage that I should mention is that we can only use pings, right? If anybody can figure out how I can invoke a DNS query from, you know, 3 billion sites, that'd be great.
Exactly. No, I like the VerfPlotter thing. What occurred to me is that one possible source of error is, of course, your geolocation. And two questions about that. A, what did you use there? And B, did you do any plausibility checks on those? And could you share those?
So the echo cut you out at one point. I think you were asking about the geolocation.
The geolocation of the hit list, basically.
So the geolocation of the Atlas data, we believed what was in the Atlas.
Oh yeah, and that is obviously 110% accurate.
So, so for the other data, we used, I believe, the MaxMind data, which is sort of the common.
So you use the public MaxMind stuff?
I believe it's the public. I'd have to ask my colleagues about exactly what data set we used.
Yeah, I would be really interested in whether you did any data quality on that, because my experience with it is mixed.
Yeah, no, it is not perfect, and I can even show you a good example of not perfect, right? Because if you look at like our B-route coverage of North America, you will see that big giant circle in the middle is where that particular database maps all unknown. They know it's in North America, but they don't, or in the United States, but they don't know where, and they center it in Ohio. Yeah. It's not because that, you know, that Ohio has that many more /24s.
Yeah, and if you look very carefully, just you know, under the Western Africa, there's this dot which is at zero latitude, 0 longitude.
Yes.
Which you always get.
Yeah,
don't get me wrong, I like the FabRouter thing, and I'd really encourage people to actually use it for something different so that we can correlate stuff. It's really a great idea.
Great. All right. Thanks, Daniel.
Okay. Thank you, Wes.
Next, we have Mr. Alexis Faskel. Alexis is the lead developer at PCH within the Recursive Resolver project. And he's involved in collecting, condensing, storing, and presenting DNS usage data for that effort. And he will talk about you today about this. So, Alexis.
Hello. Hi, everyone. Today I'm going to do a short presentation on some of the work we've been doing at PCH. A quick introduction about PCH. We're a small NGO that provides operational support and security to critical internet infrastructure. We operate in 154 POPs around the world, and today we're going to focus on two of our networks, which is public recursor network and an authoritative resolver network. So the reason for that is PCH has been started a pilot for an Anycast public DNS resolver recursor. So it aims at improving security through RPZ block lists from more than 20 threat providers. It also aims at getting more user privacy, because we are an NGO, we won't transmit or sold any information. And finally, in terms of performance, we do have a large footprint, so we are mostly close to a lot of internet users. This project means a lot of DNS traffic, which means we need to monitor it. Some of our use cases are understanding the routed nature of the queries coming in terms of transit and origin, keeping track of the DNS records so that we can do easier malware domain detection, and some also domain name monitoring. It comes with a lot of challenges, mostly scalability. We do have a lot of clusters and a lot of queries, so how do we process them? We have a lot of also resource limitation, both hardware and network, human resources and cost limitation. And finally, at this scale, the structured databases are not well suited. Finally, we have, we hope that PCAP monitoring will become obsolete sometime soon. And finally, in terms of PII constraints, obviously no client IP addresses must be stored on disk or transmitted outside a POP. So the solution we've been working on is basically really simple. It's just trying to aggregate everything at the edge and answer predefined questions. The reason for that is at this scale, we have some use cases that are not necessarily easy to solve. For instance, we'd like to be able to join BGP data and DNS data in the sense that we want to be able to find out the nature of the queries. We also need to be looking at the entire feed of data if we want to be able to keep track of DNS records and keep uniques out of those records. Then we need to look at the entire feed. One of the benefits of that is it avoids an overgrowing logging system, since we're going to aggregate everything at edges. We don't have like a central core with like lots of data on it. And so lastly, well, since we're doing distillation at the edges, we don't need that many resources at the core, but it also means that we lose some of the flexibility in answering new questions. So how do we store the data? We opted for a simple solution, which is Hsdbs. It allows us to have simple querying and visualization tools, also simple data retention techniques, and it means that tagging is really important and it must be done well. One of the pros of using a Hsdb is it's mostly easy to maintain, as long as you do pick metrics that are really important. And you also have issues with scaling, meaning that if you want to keep data for a long time, then you must average it somehow. Moving the data it's actually an interesting point. We've been using DNS Dist, which is a DNS load balancer provided by PowerDNS. One of the most important features about it is it allows us to stream all the feed of DNS queries through protocol buffers. For the purpose of our projects, we needed some kind of a protocol buffer duplication system, so like multiple consumers can have access at the feed. And that's a custom middleware. So let's take a look at the architecture. So you can see that each POP is having a Cisco machine and also multiple resolvers machines. Within that resolver machine, you'll find DNS Dist, which talks to the clients in terms of DNS data. You also find a telemetry machine where you'll find protodub, which is a custom middleware for protobuf duplication, and DNS Uni and DNS OARC that are custom softwares that we wrote to answer our questions. So if I take DNS OARC, for instance, it's going to be talking with Quagga to get the BGP feed, sorry. And it's also going to talk to protodub to get the DNS feed from DNS Dist. Combining those those two data sets, we're able to output something in a Hsdb format, which is then sent to a central instance. Same goes for DNS Uni. DNS Uni is actually aggregating at the edge and then sending aggregated data to a central instance. So let's take a look at the results and progress. So one of the best benefits of that architecture is we do make the resolving of the BGP data at the edges, so it distills lots of the data we need to move around. One feature we've built in is the ability to actually deaggregate. So if you need to actually look at the /24 or /32, you just have to put some comment, and the software is actually going to keep track of that. We still have issues with cardinality, meaning even though we do turn millions of points into low thousands of series, it's still a lot. And with like scaling and a lot of queries coming up, we might just have to go for multiple central instances. So this data set answers some interesting questions, such as who should we pair with, what are our traffic changes, what are the changes in traffic, are we seeing split origin traffic, and then, and if yes, how often, and finally, what are the authoritative resolvers that send us the most NX domain. So here's an example of a dashboard that you can get from that data set. So the first line is the top 10 no errors by prefixes. The second one is the top 10 NX domain by prefixes as well. And then you get the top 10 origin AS and transit AS on the two last graphs. So some conclusion and lesson learned. Sorry. Okay, so I'm missing a slide. That's all right. I'm just going to keep going on this. Sorry about that. So I'll just get some results as well on DNS Uni. DNS Uni has been interesting because, again, it's aggregating data at the edge. It means two different types of caching, memory caching at the edge and disk caching at the centralized instance. And it finally feeds us with a feed of DNS records, unique DNS records, that we can then send to partners so that they can do analysis on malware domain detection. So finally, we've been learning that in some cases it's interesting to have a specific architecture that answers your specific questions because it allows to actually ask the question at the edge and then distill and aggregate the data at that point. So we definitely lose some ad hoc abilities, meaning that if we have new questions, it's a bit more difficult to actually just go and ask the question. But we do have a gain in speed, and of course, it's an increase in scalability and a decrease in costs. What we've learned about Hsdbs is we can use them for complex monitoring needs. It's not necessarily just monitoring how many queries you've got. It can be joined with other data sets. But it means that you have to be really careful when you pick your metrics and you do your tagging. It must be done right the first time, otherwise you might just have to deal with it for a long time. Finally, designing the code base is interesting as well because you have to make it flexible. It means components that you can reuse, but not too much, otherwise you're just like battling with generic components and it's just too much work. So some future projects are making alternate ingestion protocols such as DNS TAP, eventually PCAP as well. We'd like to be able to do some domain name monitoring, mostly volume stats for zones. And finally, we'd like to be able to do PCAP and add them to the TSDB and summarization model we've been working with. On the metrics management and display, we've got the dashboard creation process, which is endless. And also, we'd like to be able to integrate with AI systems so that we can do alerting. Interestingly enough, I guess we could also geolocate all the Pgp data and get to a coverage as we've seen just previously in the previous talk. That's it. Any question?
Any question for Alexis? No?
Okay.
Okay. Thank you very much.
Okay, and our last presenter of this session, he is Stephan Leinhorn. He is an experienced networking professional who designs, builds, and operates large and complex networks. Stephan is currently employed at T-Mobile, where he leads a team of network and DNS architects. Previously, he managed the team responsible for DNS at Microsoft, as well as held senior leadership positions at Secure64. Stephan?
Thank you. Thank you. Yeah, my name is Stephan Lagerholm with T-Mobile. I'm going to talk a little bit different, not DNS Sec, but more around IPv6 and what we're doing around IPv6 using DNS64. So my talk, maybe I should rename it, How to Break DNS Sec for 70 million clients without rolling any keys. But we can talk about that later. I held this talk about 3-4 months ago at an IPv6 summit, and it's pretty much the same talk, although I'm going to focus a little bit more on the DNS aspects here. So do I need to click on anything here to get this to? Okay, I put it on the... I see, okay. Well, I can kind of introduce myself a little bit more and talk a little bit more about some details here while we figure it out. We have a little bit more time than I expected. I held this talk at the IPv6 summit in March, April at the LinkedIn headquarters, more focused around DNS, around IPv6 at that point. So today I'm going to talk more about the DNS aspects of it. I'm from Sweden originally. I moved to the US in 2007. I worked for Secure64 for a while. Around 2010, one of the sales guys there calls me and said, hey, T-Mobile is, you know, I'm talking to T-Mobile, and this guy Cameron Byrne from T-Mobile, and they're talking about DNS64 or NAT64. I have no idea what they're talking about, so can you call him up? So I called Cameron up, and we talked about this, and he kind of convinced me that DNS64 is, I always thought that DNS64 would be something you can use kind of in a lab or something to test your IPv6 only abilities in your clients. But he kind of convinced me that you can actually do this on a large scale. Then I went to work for Microsoft for a while, and now I'm actually working at T-Mobile closely with Cameron. So it's kind of fun to do that full circle. There we go. Okay, thank you. So you can reach me if you need to or want to ask any questions. Agenda for today, I'm going to talk about our journey to IPv6, some background about DNS64, 464 XLAT and the technologies that we are using, and then some testing of some failure scenarios that we were doing as we turned this on, and then some conclusion from there. So how many of you guys are T-Mobile customers in this room, if we get some hands? Okay, it's a pretty good crowd. And how many of you guys are using an iPhone? So, okay, so we got probably 15 people or so in here that are IPv6 only. So they don't have a single IPv4 interface on their phone if they turn off the Wi-Fi. So I think that's a pretty remarkable accomplishment, and I don't know if you guys knew that you were IPv6 only when you were on T-Mobile's network. So we really reached this utopia that we've talked about for the longest, right? We want to change the IP protocol for clients without them even knowing that we've moved them over from IPv4 to IPv6. So I think that's a huge accomplishment. And our journey to IPv6 started really with Android 4.3. That's when Android came out with support for 464 XLAT. And I'll go through the details about that in later slides. We're a little easier perhaps than most others because really we have two OSs to worry about. Yes, there's some Blackberries, some Windows, and some other stuff out there, but Apple and Android probably covers 95% of our user base. So it's much easier than, you know, the general kind of enterprise network with a lot of different stuff going on. Apple has also been tremendously helpful in this. In 2015, they announced that any app in the App Store must be able to function in an IPv6 environment to be accepted. They're doing some rudimentary testing here, but we've also found that, you know, a lot of the applications, they think that they work on an IPv6 only network, but at the end of the day, they don't, right? So they're not doing a terribly deep analysis of your IPv6 compatibility here. But to have them in the back and also them complaining to app providers have really helped flushing out some of the brokenness that we've seen historically. So as I said, our IPv6 journey started in July 2013 with Android 4.3, and then from there we've been on various talks and presented. And as you can see, it's been growing steadily to a point that as of today, or a couple of weeks ago at least, on the World IPv6Launch.org website, you can see that we have 89% of our connections coming out from our AS is using IPv6. So I think that's a pretty remarkable accomplishment, and we are the leader in the world around doing IPv6. But keep in mind what we're measuring here really is if a device is capable of doing IPv6. So it could be dual stacked, it could be 464 XLAT, or it could be an IPv6 only client. And certainly the tougher piece is to go to IPv6. So even we're the leader, but I also believe that we're the only one who's actually running our iPhones in an IPv6 mode in the world. I know Reliance in India is doing some experiments, and I don't know if they've turned it on yet, but they're pretty close. And Verizon here in the US is also doing a fairly good job of enabling IPv6, and they're around 83% of their client base is IPv6 today. So the remaining 11%, some of them are, yes, are enterprise clients. Just like anybody else, we have an office environment. It's a little bit harder to turn on IPv6 there, and we really started with the big problem, which is the handsets, and now we're working on trying to enable IPv6 on our enterprise, on our Wi-Fi, and so on. So this will take quite a bit of effort and several years probably to get to a point, but hopefully we'll get our first kind of guest Wi-Fi experience coming up pretty soon. We're also eyeing what Comcast is doing in Philadelphia. They have a new office building there that they're saying they're going to go IPv6 only using NAT64, DNS64. Cisco down here is also using IPv6 in, I think, building 23 or something, IPv6 only on their enterprise network. And Microsoft up in Redmond is doing some trials also with IPv6 only. So this is something that hopefully we can learn from them and see what do we need to do and what are the problems in a more enterprise environment when you have a more diverse base of OSs and printers and other things that perhaps might be a little trickier to turn on IPv6 on. There's also the really old handsets, obviously. If your grandma has some old Android phone from 2005, then it's not going to work with IPv6, right? So we might see some of those, and they're being flushed out, as time progresses. Also, when you do tethering, so if you tether your laptop to your phone, then your laptop is going to be presented with two IP addresses, one v6 and one v4 address. And you're actually going to go through double NAT in that case. So your phone is going to NAT you one time, and then as you go out and traverses towards the internet, you end up with another NAT session there. So that's wonderful, but that's how it works. You can, of course, use the v6 interface, and you don't have to worry about it. We also have MVNOs, mobile virtual network operators, and people roaming into our network, like TracFone and others that, it's not guaranteed that they will always have IPv6 for various reasons. And also keep in mind, we're talking about a wireless network, so if you drive 60 miles an hour and there's a big building there, chances are that a packet might get lost and you might retry, and with the happy eyeball technology, that retry might be a v4 retry. So I think it would be a little bit easier if there were no retries. I think some of this 11% is actually retries as well. So just a recap, I believe that we at least have one author of the RFC for DNS64 here in the audience, so I'm not going to go too deep in this, but I think a recap for everybody is to understand how this works. So we have a v6 only handset that attached to the network, and as it wants to talk to something, it sends out the DNS query. And if there is an IPv6 Quad A record available, we send it back, and the client goes out in the kind of black path directly to the v6 internet. And that's the ideal path because we're not going through any NAT boxes or anything here. So ideally, that's what we want to accomplish. But in the case where there is no IPv6, there is no Quad A record, instead of just sending back the A record, we do a synthetic Quad A record. So we have a DNS64 prefix, and then we append the IPv4 addresses at the back there. So you can see 192.0.1.1 there. You convert that to hex, it's going to end up being C000.101, right? So we append that and put the prefix and send it back. And that really tricks the handset into going v6 only to the NAT64 box. And then we do the translation back to v4 on the NAT64 gateway. And that's what's marked in red here, which is obviously a more cumbersome and more expensive path to go down. These boxes are not, they're rather large. They need to keep state. So they need a lot of memory and CPU, and these are specialized boxes, and we have quite a few of those. So, we would rather have people go directly out to the internet on a v6 as opposed to going through these boxes, right? But the interesting thing is, as you deploy IPv6, and the usage for us on IPv6 right now is not determined by anything we can do, pretty much. But it's determined about how much content is out there that's available over IPv6. So as we see more and more content gets v6 enabled, we see how our NAT64 sessions goes down in our gateways as people go directly to IPv6 instead. So once NAT64 got deployed, the initial idea, I think it was for everybody to use just NAT64 DNS 64 as a transition mechanism. But it turned out that there were some problems with this, and there's applications and websites with IPv4 literals, so they have hard-coded IPv4 addresses for one or another reason inside of the, oh, I thought I had only 10 minutes left. Okay, okay. IPv4 literals embedded into their applications. And that obviously didn't work if you don't have any IPv4 interface. So what 464 XLAT draft is all about is to create kind of a virtual IPv4 interface. So there's a CLAT daemon that's running on the handset there all the way to the left. And then you're doing translation from there 4 to 6, and we transport it over our network as an IPv6 packet, and then it hits our normal NAT64 gateways, and we do the translation back from there. So it works very well, and it gives Android handsets an ability to, even with broken applications with embedded IPv4 addresses, they have a way out on the internet, right? But normally DNS64 is kicking in and working, so this is only being used for that scenario. There are some rumors about 464 XLAT for Windows 10 coming, so we'll see how that goes. It's actually enabled today, and there's a blog post from Microsoft around this, but it's only if you have a SIM card and an LTE modem in your laptop, which very few laptops have today, unfortunately. But we'll see, maybe in the next update in Windows they will have it. I think it would be a good addition for enterprise kind of scenarios. So you can hard code the DNS64 prefix in the Android device, but we want to use this discovery method instead, so we don't have to hard code anything. And we're actually using different DNS64 prefixes in different regions across the US. If we were to use the same prefix, we would have to anycast our NAT64 gateways, which we were a little bit worried about doing that. So instead we decided, yes, to have different prefixes, and it gives us a little bit better granularity, and we can move stuff around a little easier. If there's an issue in Dallas, we can move everything down to Houston, just by providing them the Houston prefix instead, and all the traffic would go down there, for example. But you can do this discovery, RFC 7050, where you send a DNS query for IPv4 only.arpa, and from there you get a response, and this is a guaranteed to be an IPv4 only response you're getting here. So if you get a response when you behind NAT64, you know that the prefix, this is a translated, so you can extract the prefix and just throw away the IPv4 part and extract that prefix and use that. And this happens during startup of Android devices. So they send this IPv4 only.arpa, and they extract the prefix and they use that for their sessions. And then there's the happy eyeball draft that I want to mention also a little bit about. You know, it gives a fallback to IPv4 after a reasonable time. It works very well in dual stacked environment and with 464 XCLAT clients. We got to remember though that happy eyeballs has zero effect on IPv6 only clients. So if you're running an iPhone on our network, which we have about 10 million of those, then there's no effect on happy eyeballs because there's nothing to fall back on. There's no IPv4 address to fall back on. There's a new version of happy eyeballs being worked on in IETF, and there's been a lot of discussions on the mailing lists around that. Personally, I don't know. I mean, you can change the timers a little bit and perhaps get a little bit better user experience, but I don't know if it's really worth it. to do anything. That would be my personal opinion, but I think it's a good draft. You know, it probably should become an RFC. There is some saving grace in Apple actually for IPv4 literals. If you have something embedded in a website or if there's an application, if you happen to use, and I realize this is a little small, but in blue there in the middle, it's the Apple APIs. So if you have developed an application and using the APIs from Apple, like NSURL session, then actually what's going to happen is that Apple will do the RFC 7050, and it will going to get the prefix and actually do that translation for you and send it to our NAT64 gateway. So you have a little bit of a chance in Apple if you're using their APIs to actually get it to work even with IPv4 literals. But if you go and do socket level programming like the red and you're using the kind of raw sockets, then of course if you have an embedded IPv4 address, then in your application it's not going to work. And there's a link here people can click if you guys are interested in knowing more about that. There's a lot of applications you can download if you want to see your addresses that you have on your phone. Network Info 2 is one that I've been using a little bit. And in this use case, I'm tethered, so I actually have a tethered IPv4 address. I got an IPv6 address. We're also using voice over LTE, so you'll see two IPv6 addresses. One is for the internet, another one is for VoLTE. So when you make a phone call, it's going to use the VoLTE address and communicate with our IPv6 gateways for that. So don't be surprised if you see two IPv6 addresses there. And then, if you have Wi-Fi enabled, you'll also see, of course, the Wi-Fi addresses, and then also a 464 XLAT address there if you have an Android phone. So this will not be available if you have an Apple phone, but on an Android you'll have this 464 XLAT. And you can identify that. I think it's 192.0.0.4 or something like that is the IPv4 address for the 464 XLAT interface. So I want to talk a little bit about failure scenarios here, and there's really two groups of failure scenarios. So we were a little worried when we were turning on IPv6 only. We didn't know how many failures we're going to have, what kind of complaints we're going to have, and actually we ended up rolling back 2 times before we turned it on. So we turned it on about a year ago and had to roll back, and then we turned it on in kind of January timeframe and rolled back again. And then somewhere in March, April timeframe, we turn it on, and it's been staying on since then. There's the network-related failures. So people that put special use IPv6 addresses as a quad A, ::1, for example, it's not going to work very well, even if you have an IPv4 address in there that works, right? So in our case, there's nothing to fall back on an IPv6 only iPhone, so we're dead in the water if we get presented with something like that. There's also the routing. If you put something quad A that doesn't route, then there's nothing to fall back on. Normally you'll be saved by happy eyeballs, but obviously there's nothing we can do if you present us with a quad A that we can't route to. And this is one of my favorite, or I don't know if I should say favorite, because I'm from Sweden originally, as I said, and www.ericsson.se. You cannot reach that from 10 million iPhones within our network. It's impossible, because they have a bogus IPv6 in there that routes to nowhere. And dual stack clients, they will fall back to an A record, but an iPhone that we don't have a v4 interface, we cannot reach it. So if anybody knows anybody at Ericsson and can try to reach out, I've tried via LinkedIn and Twitter and other means, but so far I haven't made any progress. But feel free to try, you guys that had your hand up here with an Apple iPhone, try to go to www.ericsson.se, you'll see you won't be able to get there. So those are network-related failures. The good news with the network-related failures is that they're pretty easy to troubleshoot, even for a NOC or a more junior engineer. Traceroute, ping, and those kinds of tools you can use and you can see. So if somebody calls us, we can detect and help them pretty quickly with that. The other group of failures, the DNS-related failures, are much harder to troubleshoot. I would say there are probably a handful of people within T-Mobile that really would understand and be able to help somebody with these types of problems, trying to figure out what is going on. So there's 4 types of issues here. And initially, I was concerned and thought that this would be a big problem. But I got to say, as time has progressed, I'm no longer that concerned that we really have a problem that we need to go fix here. But let me walk through some of them. So we have an R code issue. So the RFC actually says that regardless of what R code that you're sending back, you should do the synthetic transaction. So if you get a form error or not implemented or something like that, you should actually do the synthetic. But it appears that a lot of recursive resolver doesn't do that. So that's the first. It's fairly rare, but there's some use cases around this out there. There's also the flag. If you don't return the AA flag in the response, then some recursive resolvers derails and they don't continue doing the DNS64 translation. And this is a little annoying because typically the recursive resolvers, they've hardened the normal, the happy path, the IPv4 path, and they take into account a lot of misconfigurations like sending records with not the AA flag set, and they accept that. But in terms of DNS64, they do not, right? So it creates this difference in how the recursive resolver is handling DNS64 versus regular queries. We also have the SOA problem. A lot of sites, load balancer type of sites, they don't return the SOA record in the empty no error for the actual domain that you queried for. So they return something completely different or something higher up in the domain hierarchy. And that also makes some of the recursive resolvers derail. So this is somewhat common. We had a photo site in Germany that I reached out to, and actually they fixed their problem once I reached out. So they're very happy that we told them that they had this problem. And then the most common DNS-related failure is probably timeouts. So you ask for quad A, and you don't get anything back. And then, happy eyeballs on a dual stack environment would take care of it, and you get something. But in terms of v6 only, there's not much we can do, right? So www.sky.com.mx is a good example of a site like that. It doesn't return anything for quad A, but it returns fine for A record. So it's problematic to get that to work on our network. I created a little test bed, so you can try. This is with the Google DNS64 service. You can do a dig towards it, and then SOA or flag or R code or timeout.dns64.lagerholm.com for quad A. So this is just a little Perl script that's running there, and it's going to then simulate these failure scenarios, whereas the A query is going through fine. So expected result, for example, if you do a dig for timeout.dns64.lagerholm.com, would be that you get quad A record back, right? So we managed to do the DNS64 synthetic transaction. So you'll see the DNS64 prefix, and then I put 100.100.100.100 as the IPv4 address, so you get 64.64 as a result back there. So you can test your own recursive resolvers, your own implementation, and see how it works on DNS64. Here's kind of a breakdown of some recursive resolvers. We're using Secure64 in our environment and Bind. Also the Google DNS I've tested early this morning, and also a little bit older version of Unbound, but I don't think there's been any changes in the DNS64 behavior. So the SOA, I think, is actually the R code is the one that I'm most concerned about, because really the RFC is pretty clear and states that whatever the R code is, you should do the DNS64 synthetic. And if we have a client that calls us and have this problem, we really got to fix it for them, because we're not RFC compliant. We managed to strong-arm Secure64 since we're a customer into fixing this bug for us. So they used to Surfail, but they're not doing okay. Google DNS64 is a little bit all over the place. Some stuff is handling better than others. The flag in SOA, it seems to be sensitive for. Unbound is doing fairly well, actually. I would say that's the one that's doing the best. It's doing okay on the SOA and the timeout failure scenario, the flag failure scenario. But for timeout and R code, on the first query, it actually sends a timeout, or it doesn't respond. But then on consecutive queries, you actually get a response out from them. So it's just like an initial hiccup there for some reason. It puts it in the cache, but it doesn't send it back on the first query. And I'm not a C programmer, so I haven't been able to fix it myself. I know the line, and I think I know what to do and where the bug is. But maybe somebody can help me, and we can figure it out over the social event or something. Most applications have really used there was an open source implementation of DNS 64, I think called Viagini or something like that. A Canadian guy came up with, and he contributed these patches to both Unbound and Bind. So I think they're kind of based on the same kind of library, but then it moved around from there to in different directions, and you know, so it's a little different how they respond today. So to conclusion, DNS 64 with or without 464 XLAP, I would say works very well, and it scales to 70 million customers that we have at least, which I think is one of the largest service providers in the world. So I don't think we have to be worried about the scalability aspects of it. It's an unfortunate side effect that, yes, we do break DNS Sec. So if you're running like a DNS Sec trigger or something on your phone or on your laptop, it probably wouldn't work that very well. We could do DNS Sec. We don't have DNS Sec turned on on our recursive resolver. We could turn it on there potentially and do DNS Sec. And you know, I think this is something that needs to be figured out long term. You know, I'm concerned that we're doing this, right? It's an unfortunate side effect, but you could potentially do an RFC 7050 query, get the prefix, and then as you do validation, you strip the prefix and then do validation on the kind of A record that you're getting back after you strip the prefix. So it's not we're lying, but we're being upfront with what we're lying with, right? So you could figure it out. You could figure out if you really wanted to. And when we turned IPv6 only on, some of the stuff that we did was to determine what sites and apps are important. We did scans, you know, Alexa top 1 million, and we found a lot of sites in China and Indonesia and India and stuff that we deemed we're not going to waste our time to try to reach out to them, to try to have them fix it, because it just doesn't matter to our client base, probably, right? But we reached out to a lot of universities and a lot of, we had a couple of universities that were broken, and a couple of large, one large cloud storage type of provider that was broken. They had to go fix their application. So we fixed a lot of stuff, and I feel like we've been paving the way a little bit here. So I hope more people jump on this DNS 64 bandwagon, and really, so we can get the usage of IPv6 up a little bit. Don't try to fix things with local overrides. We had actually a Visa issue, kind of a bank that had issues, and initially we thought maybe we'll just put in an override and just do the synthetic forum, so to say. But we realized that, you know, it opens up huge liability if we start redirecting, you know, Visa, credit card stuff left and right. You know, it's probably nothing we should want to be involved in, right? So we stopped doing that. You probably shouldn't want to do that, even if you could. And then scan social media for direct customer feedback. As I said, we're only a handful of people that can actually kind of troubleshoot this stuff, and it might be hard to get through to us, right? So, but if people are complaining on Twitter or Reddit or something, we're kind of lurking there and seeing if we can see anything, and we try to help them. Don't try to change the world, you know, as I said, if there's a broken site in Indonesia or something, it's not gonna, if we want to go IPv6 only, that's not gonna stop me from doing that, right? And we're big enough to kind of create an impact and be first in the industry here to do this kind of stuff, right? And then hopefully we're working on an enterprise kind of rollout now to see what we can do on the enterprise side of things. We have a lot of IPv4, and we're running out of RFC 1918 space internally and stuff, right? So we have a lot of work to do there. That's what we're going to focus on here moving forward. So with that, I'm open for a couple of questions. I believe I have a few minutes for that, right?
Any questions?
I'm Jim Metatier at Influx. I'm wondering about failure you've seen. I guess some of them, especially the timeout, can easily lead to angry customer calls and so on. And have you seen many complaints or not?
We've seen a few. We've seen a few kind of load balancers and stuff that have the timeout issues. We're not gonna. I mean, there's nothing we can do on our side, right? They have to fix their recursive or so their authoritative server to actually present. Either you present an empty no error, and we'll do our own thing with DNS64, or you present an IPv6 address in a format we can consume. But the problem is when you don't like an iPhone is only going to send out a query for quad A. It's never going to send out a query for an A record to begin with. So there's nothing to fall back and nothing to do for us, right? So they really have to fix it on their side, and that's the kind of stance we're taking on these kinds of problems.
And customers accept that.
Well, I don't know what to do. I mean, you know, I think T-Mobile, we're large enough that we can take a stance in one direction, and, you know, I don't know what to do. Like, I can't help Ericsson.se, I can't help them, you know. It's like, I don't know what to do. I mean, these problems exist, and they need to fix it on their side. There's nothing wrong on our side. We're RFC compliant on our side, right? So.
All right, and also as a related information, my understanding of the version 2 of Happy Eyeball introduces some resiliency for the timeout issue, and iOS should already have that. And if I don't know about the status of the Android, but if it also supports that, it may change the situation.
Right. There's two different timeouts here, though. We got to be clear. Happy Eyeballs is helping you in a dual stack type of environment where you have both v6 and v4. And you get those two return in DNS, and you try to connect HTTP, and you can't connect for one another reason. You're going to try with the v4, right? The timeout I'm talking about here is a timeout in DNS. Yeah. You send a query, quad A query to DNS server, and you never get a response back, so your recursive resolver times out, which is slightly different, right? So,
yeah. So I'm expecting a possible change in the Android implementation in that sense, and you may also notice that in future, or already.
Yeah, I didn't really get the question.
The timeout of the Android implementation for the DNS may change.
It might with the Happy Eyeball draft. They might implement that, and
that would be interesting.
Yeah.
Thanks.
Thank you.
Paul Hoffman, ICANN. So you're a big mobile provider, or you are now. You've been Microsoft in the past. Which other big mobile providers, if you had swapped into some others, are doing this much, or are you way ahead? Are you sort of on par with others? Are you really far ahead?
I think I don't really know. I spoke to the people at Reliance in India because I know them. They said that they're eyeing turning off IPv4 for iPhones, but they haven't done it yet. Mm-hmm. And I'm not sure about Verizon, whether they have done it or not. They're doing fairly well in terms of IPv6 in general, but I don't know if they've turned it off yet. So I would say we're ahead. We were the first one out doing this, and we turned it off in, you know, April kind of time frame. So we've been having it off for about 6 months for around 10 million iPhones.
Because the side effect of that I'm interested in is what do your in-house recursive resolvers that all your customers are going to, how is that affecting that? Are you getting something funny in your caches, because your caches are all now quad A records and such like that? Not that you can answer that now, but I would be interested across recursive resolvers who have a feature that we're not used to. What kind of things are we seeing? So if you can find that and let us all know, that would be great.
Yeah. I have some data. We do definitely have seen a decrease in DNS queries because the 10 million iPhones now, they're only sending quad A queries. They're never sending any A queries. So we did see quite a drop. But we have about 20% iPhones, right? 80% Androids. So it's not that significant anyway in the grand scheme of things. But you can definitely on a graph see it. You see a drop as iOS 10.3 got rolled out. You could see that drop.
And
sure.
those customers of yours, go to your normal recursive resolvers. You don't send them to quad A result. You know,
it's like two views on one server, if you wish.
Okay, great. Thanks.
So, yeah.
Hi, I'm Andrew Sullivan. First of all, I want to thank you for deploying this, because I got to be honest with you, when we worked on DNS 6.4, I had no expectation that it would ever scale this well.
Me neither.
So that's really great news. I sort of thought, maybe the size of this room, but this is really very pleasing. But the question that I do have is whether there are pieces of that RFC that need significant clarification, because I haven't had a lot of feedback from people who've implemented this, and if there are chunks of it that need work, that would be great to know, because then we could produce, like, I'm not going to work on another document for no reason, but if people need help, then I'm happy to do it.
I mean, it's these four, there's failure scenarios definitely that's not defined in the RFC that probably would make sense, because it's hard for me to go to a vendor and say, hey, go fix this if there's nothing in the RFC. If there's an RFC saying that they need to have this, and we bought the product on the premises that they would have support for this RFC, it would be easier, right? I think it would be useful to have a BIS version of DNS 64 at some point. I think so, especially the R code. I mean, the R code is already there. The other failure scenarios, there's no mention of them. So I think it would be useful. Although I want to put everything in perspective. There's a lot of shit that's broken on the internet, right? So in the grand scheme of things, these small little corner cases I don't know if it's worth really working on.
Right. And the one other question that I had was the DNS Sec Support. I mean, you sort of said you're not doing it, but I guess the question is, have you tried it at all, or is it just completely mystifying? Because that part of the document is enormously confusing to me, and I wrote it.
Yeah. So in our own recursive resolver, we could turn on DNS Sec. There's nothing preventing us there from a DNS 64 perspective. It's more of a political, why do we want to do it, and what's the value, and blah, blah, blah. I think we'll get there. Probably wait until the key is rolled over, and then maybe from there we'll tackle that. But it saddens me that there's no good way of doing DNS Sec on the client behind DNS 64, and that's something that maybe also I hope we can, with the RFC 7050 and sending this IPv6 only ARPA to extract the prefix, it should be doable to implement in a recursive, like a DNSSEC trigger.
Yeah, so you can actually do it. The mechanism is there. It's just very hard to understand. But the prefix discovery didn't exist at the time, right? And we wanted to get the thing out the door.
Yep.
So okay, that's very, very helpful.
Yep.
So thanks a lot.
Yep. Thank you. Thank you. All right. Thanks everybody.
Thank you very much. Thank you. This was the first session of operations in DNS. We're going to have Keith with some announcements for lunch.
Okay, thank you, Maurizio and Pete, for chairing the sessions this morning. Okay, very few quick announcements before lunch. Lunch itself is downstairs in the Club Regent room, so you want to go out the back door, turn right, down the elevators, and then I think it's on the left in the lobby. Please make sure that you wear your badges. There's exactly enough lunches for people. The room here will be left open. There will probably be somebody in the room, but you don't necessarily want to assume that, so please modulate your OPSEC of your equipment accordingly. The surveys, we're doing a survey each day for feedback on the talks. You can complete that as you go through the day, so we'd love to hear your survey feedback on the talks. Sorry, just one other thing about lunch. If you have any questions about allergies or food preferences or restrictions, then please speak to the staff at the back of the room. We will restart from lunch at 2:30, so if everyone can be back here promptly, that would be appreciated. And finally, don't forget social tickets. If you didn't get a social ticket and you're planning to go this evening, pick it up at the registration desk. Thanks.